The topic for today is fundamental concepts of engineering mechanics. Let's have a bit of an introduction first. So engineering mechanics is the science which considers the effect of forces on rigid bodies. It is divided into two, statics and dynamics. So statics focuses on the effect and distribution of forces on rigid bodies, which are and remain at rest, while dynamics focuses on the motion of rigid bodies caused by forces acting upon them. So for us, our course, we're focusing on statics, and then the next course that some of you will take is dynamics. So let's talk about some of the concepts and their definition. First is the concept of rigid bodies. So that one definition of rigid body is that it is a definite amount of matter, the parts of which are fixed in position relative to each other. A simpler definition of a rigid body is that it's an idealization of a body that does not deform or change shape. Now, actually, solid particles are never rigid. They deform under the action of applied forces. However, in many cases, this deformation is negligible compared to the size of the body. Therefore, the body may be assumed rigid. For example, we have your steel columns. Okay. These steel columns may be considered rigid, even though it experiences deformation, because its deformation is very little compared to its actual body. Okay? But for the purpose of our discussion, we consider most bodies as rigid, even though in actual it's different. The next concept is force. So when we talk about force, we talk about one of two things. First is the external effect of a force, and then next is the internal effect of a force. So external effect of a force changes or tends to change the state or motion or state of motion of a body, while the internal effect of a force produces stress and deformation in the body. Look at the images to the right. So as you can see, if we're focusing on the change in direction of the ball as it is being hit by your baseball bat, we're calling that the external effect, the change in motion. However, if we zoom in and if we focus on the way the ball deforms as it is being hit by your baseball bat, then we are considering the internal effect of force. In general, external effects of forces are considered in engineering mechanics, while internal effects are in strength of materials. Okay? We are mechanics, therefore, we're focusing on the external effect of a force. In your succeeding courses, we'll talk about strength of materials. Okay? Especially in your MEC32, that's your strength of materials. For now, we're focusing on the external effect of a force. Now, generally, a force has three characteristics: magnitude, position of its line of action, and direction. Magnitude and direction are pretty easy to understand. So let's focus on position of its line of action. Okay. So position of its line of action is just the path of which your force takes or follows. Within that, we have the principle of transmissibility. It is stated there that external effect of a force on a body is the same for all points of application along its line of action. Let's take the following as an example. For example, here at the top, this force is on the left side of your block. The effect of this is equal to this, wherein the force is at the right side. So even though this is a push, this effect is equal to a pull on the body. Another example is here. If your force is applied at the base of your figure, this effect has the same effect as it is when the force is applied at the top of your figure. Another example is this. We have three forces applied at the surface of your ball. This effect has the same effect as when all the forces are applied at its point of intersection. Okay, so that's the principle of transmissibility. As long as it follows the line of action, okay, so you can see the path your forces take, the effect is the same no matter where it is applied, whether it is here at the left side, right side, bottom, top, etc. However, this is only correct if we're talking about the external effect of a force. It's different if we're talking about internal effect. Internal effect, again, is the deformation. The internal effect of a force is definitely dependent on its point of application. For example, here, if this is your point of application, deformation will happen here at the left side of your block. It's going to be compressed. If the force is applied here, it's a pulling force. Therefore, instead of a compression, this side will experience an extension. So as you can see, the deformation is different. So once again, principle of transmissibility is only applied to the external effects. Okay. Next, we have your units. We have your pound. We have kip, which is just 1,000 pounds. We have a ton, which is equal to 2,000 pounds. G for gram and kg for 1,000 grams. Kip and ton are some of the units that you might not be familiar with. So now, and you'll know that when we talk about kip, that's just 1,000 pounds, and a ton is just 2,000 pounds. Okay? So that's it for the concepts and definitions. Now let's talk about force systems. So a force system is any arrangement where two or more forces act on a body or on a group of related bodies. Under that, we have these types of force systems. First is your coplanar. So coplanar is when the lines of action of all the forces on a force system lie in one plane, hence coplanar, all of them in one plane. Next, we have collinear force systems, forces which have a common line of action, hence and collinear, same line. Next, concurrent force systems, forces whose lines of action pass through a common point. All of them intersect. Parallel force systems, forces whose lines of actions are parallel, self-explanatory. And then lastly, we have your non-concurrent force systems, forces whose lines of action are neither parallel nor intersect at a common point. Now, for this, non-concurrent force systems, some of the forces may intersect, some of them may be parallel, but not all. Okay? So this doesn't mean there won't be any concurrent or parallel force system. It's just that all of the forces involved are not parallel nor concurrent. Let's look at some examples. Here to the left, we see a game of tug of war. Okay? The left side exerts a pulling force to the left. The right side is exerting a pulling force to the right. This force is along the rope that they are holding. Okay? As long as it is kept horizontal, this pulling force to the left and right are both along the rope. Therefore, this is an example of collinear force system. Okay? An example of your concurrent force system is your cable cranes. So you have your crane. As you can see, these are the cables experiencing tension force. These three cables intersect at this point. Therefore, the forces in those cables also intersect at this common point. Therefore, they are concurrent. Next, we have a bridge. Now, for a bridge, if you recall in your physics, if you talked about it, if not, for a bridge, forces are present in each member, okay, in each of these parts. Therefore, imagine cutting through one side of your bridge. You can see how forces interact. These two forces will intersect. However, this will not intersect with those two. Okay? These two are parallel, but not all of them are parallel. Therefore, this is a non-concurrent force system. However, if you look at the joints, okay, the joints are where your members intersect. Obviously, since the members intersect at that point, the joint is considered a concurrent force system. Okay? And then lastly, if you have a group of objects together, in this case, we have an apple or apples. If you consider their weight, okay, weight is always downward. Okay, no matter the scenario, remember weight is always downward. That's the force of gravity. So if you consider the weight of each apple, all of them are downward, all of them are at the same direction. Therefore, they are parallel. Okay, so those are some examples of force systems. If we draw a sketch or what we call a free body diagram of those forces, we will have something like this. So collinear along the same line, concurrent intersecting at a common point, non-concurrent, neither concurrent nor parallel. And obviously we have parallel having the same not orientation, rather direction, whether upward or downward, left to right. Yeah, they're still parallel. Now I've mentioned free body diagrams. Let's talk more about that. So free body diagram is a sketch of the isolated body, which shows only the forces acting upon the body. Okay. So it is used to distinguish between action and reaction forces. The forces acting on the free body diagram are the action forces, also called the applied forces, while the reaction forces are those exerted by the free body upon other bodies. So we have two forces here, action and reaction. Action is just the applied force. If we have a body, any force applied to it is your action force. And then the reaction of that body to your action force is obviously your reaction forces. So to illustrate, we have this. So the free body may consist of an entire assembled structure or an isolated part of it. And let's look here. This is what we call a derrick. Okay, so this is a derrick. A derrick is a lifting device, usually seen in ships or at docking facilities. Okay, as you can see, it lifts this weight. So there's no applied force here, right? There's only a weight creating tension in these wires. So if you draw a free body diagram, you can take this as a whole and draw the free body diagram of that, or you can take its parts. For example, here, okay, instead of taking it as a whole, we just consider this point C. Okay, so this is a free body diagram of point C. To draw a free body diagram, we're gonna indicate the forces involved. So whenever you have a cable, rope, string, etc., that usually has tension forces. Okay, so we have forces along the wires. So therefore, draw that as tension forces. Tension is always away from your point. That's why it is drawn this way. So we have tension here and tension here. Another thing is we have a reaction force from this pole. That's why we have this force P. So that is your free body diagram at point C. You can also get a free body diagram of an entire part. For example, here, we took this mast and this pole. Okay, so this is the free body diagram. Now, usually, whenever we're creating free body diagrams, we consider the supports. In this case, these are your supports. We have one here, we have one here, we have one here. So there are supports in those areas. So looking at the free body diagram, since we're not considering this, it's not shown. We're only considering these two parts. Yeah. So we have a reaction upward and downward. Here, okay, the upper support only prevents horizontal motion. That's why the reaction is only horizontal. However, here at the bottom, it also prevents horizontal motion. That's why there's a reaction along the horizontal direction, but it also carries the weight of the structure. That's why we have a reaction upward, reaction to its weight. And as I've said earlier, whenever we have a string or anything of the sort, we have tension forces. So there's tension force here, and then there will be tension force here. Okay, so that's how you draw your free body diagrams. You'll learn more about it later on as we try to solve for problems. Okay, so that ends the introduction or fundamentals of engineering mechanics.